So this is section 6.2, theorem 6.2.3. So I didn't do a video on it, but just as a reminder, theorem 6.2.2 says if A has n distinct eigenvalues, then A is diagonalizable. Okay, so so that was just the generalization of theorem 6.2.1, where they did it with 2x2 matrices. And so now, though, in 6.2.3, it says if, and they turn this thing around all of a sudden for some reason, but, if the determinant of lambda I minus A, so instead of saying A minus lambda I, they're doing lambda I minus A. So it's still that same characteristic polynomial. Might be the negative of it, but we're setting it equal to 0 anyway, and so you can multiply through by that negative. So they're saying, okay, if this is made up of these factors, so they have one root but some multiplicity. It might be 1, but it might be 6 or something like that, and then minus C2, N2. So this thing factors into all these different factors, but again, some of them may be multiple factors. Okay, if the determinant of this thing, or the characteristic polynomial, can be written like this, where, now in some ways, I don't know that these truly have to be distinct given what we're going to say, but why would you write them, otherwise if they aren't distinct? So where C1 to CT are distinct, okay, so, and then the nullity of CII minus A, well, actually, let me put that in parentheses instead of saying of that way. Nullity of CI minus A is equal to the multiplicity, so Ni. If that's the case for each of them, then A is diagonalizable. That's what they're saying. Diagonalizable. Okay, that is, we can choose some, even when we have a multiplicity going, we can choose some independent vectors to make for the null space of this thing, so that we can still get the right number of eigenvectors and eigenvalues. Okay, and then the way we would write A in this case is, or if we took P inverse A, P in this case, what we would have is what we call a block matrix. So we would get C1 times I, and here it really does matter that I put a subscript on there, Ni. So this is a N1 or N1, C1 times I, N1. This is a N1 by N1 identity, all times C, and then a C2 I, N2, and so forth down to CN, CT I, NT. And this stuff would all be zeros out here. Okay, so let's look at an example. You know, they just mention this, but they don't give us any example. And I'm going to look at two different matrices that both have the same eigenvalues. And so I'll first look at A, that has is the matrix 2, 1, 1, 0, 1, 0, 0, 0, 1. Okay. And without going through the characteristic, well, actually, it's probably worth going through the characteristic polynomial. I know the eigenvalues here are lambda 1 equals 2 and lambda 2 equals 1 with multiplicity 2. Okay, and I can see that because I've got 2, 1, 1 right down the diagonal, and this is an upper triangular matrix. Lower triangular would be the same way. I can just read the eigenvalues right off the diagonal. And we'll see that when, if I take the determinant, 2 minus lambda, 1, 1, 0, 1 minus lambda, 0, 0, 0, 1 minus lambda, whoops, straight line. Then notice that you get, you'll get the 2 minus lambda times the other diagonal elements, because when I do that determinant, I'll have the 1 minus lambda times the 1 minus lambda. But then, going this direction for that 2 by 2 determinant, I will get 0, not because of that 0, but if it's upper triangular, this is going to be 0. And so that's 0. Now when I move to this element, notice I'll get 2 zeros here. When I move to this element, I'll still have those 2 zeros there for that determinant. And if you could do an induction thing and go up in size, and you would see that this is our characteristic polynomial. We set that equal to 0, and so we get lambda equals 2, lambda equals 1. And if these were distinct, I would get all three from that. But you see, an upper triangular or lower triangular or a diagonal matrix, I can just read off the eigenvalues from the diagonal. Okay, so those are our eigenvalues. Whoops. So lambda 1, lambda 2. So now, if I do my lambda 1 equal 2, then I will get this augmented matrix. I'll have 2 minus 2, 1, 1, 0, 1 minus 2, 0, 0, 0, 1 minus 2, augmented with 0, 0, 0. So that becomes 0, 1, 1, 0, minus 1, 0, 0, 0, minus 1, augmented with 0, 0, 0. What I could do is just, swap this row with the top row, and then swap this row with the second row and multiply through by -1, so I can do a few row operations at once to get 0, 1, 0, 0, 0, 0, 1, 0, and 0, 1, 1, 0. Now, I don't know if I really needed to switch, yeah, okay, we got everything there. But I definitely, it was good to do that switch and do the negative of it. Now, if I subtract the top row from the bottom row, then I get 0, 1, 0, 0, and 0's down there, 0, 0, 1, 0, 0, 1. And then, of course, subtract the bottom row from the second row, or the second row from the bottom row. You get the same thing either way. 0, 0, 1, 0, 0, 0. Okay, this implies then that y equals 0, z equals 0, but x can be anything at once because it's just multiplied by 0. And so that means my eigenvector going along with 2, I'll call it my x1 eigenvector, is the transpose of 1, 0, 0. And again, I could use 2, 0, 0, 10, 0, 0, whatever. But I get 1, 0, 0 for my first eigenvector. Now, let's look at our lambda 2 equals 1. And that augmented matrix, I have 2 minus 1, 1, 1, 0, 1 minus 1, 0, 0, 0, and 1 minus 1. So this is a pretty quick one. I get 1, 1, 1, 0, and then everything else is zeros. That's what I call quick row reduction. And so you see this says x equals minus y minus z. So notice that the nullity here of A is equal to 2, right? I've got those two columns, or the rank is 1, and 3 minus 1 is 2. So the nullity of A is 2, which matches the multiplicity. Okay, so it matches the fact that we had 2 of those. So it says I should be able to get out of the null space, so n of A, I should be able to generate that null space from 2 independent vectors, because the nullity is 2, or the dimension of the null space is 2. Well, if I let y equal -1 and z equals 0, that would give me 1, -1, and 0. But if I let y equal 0 and z equal -1, then that gives me the vector 1, 0, 1, -1, sorry. And those are, hopefully by now we can see those are obviously independent. And so, there we go. There are my 2 vectors. And so what that says is my P is equal to 1, 0, 0, 1 minus 1, 0, and 1, 0, -1. Like that. And better yet, I could go to a unit vector kind of thing. So I would have 1, 0, 0, 1 over the square root of 2, minus 1 over the square root of 2, and 0, and 1 over the square root of 2, 0, and minus 1 over the square root of 2. So I could do that as well and call that Q usually in a lot of text, if the columns are unit vectors like this, um, and actually if we were to check the dot products of these vectors, we would see um, oh wait, well, with the multiplicity, that's probably not the case. I was going to say with that they're orthogonal, but they are not. So yeah, let's with the multiplicity thing, let's just not worry about this for now. Okay, so so we have our P there, and what the heck is P inverse? I did not look that up, but notice this is a upper triangular matrix, so we should know that. Inverse off the top of my head, not so much, but so P inverse, I believe that'll be 1, minus 1 down the diagonal. And then, actually, it might be itself here. What happens if I take this P inverse, in other words, P times P? What happens with that? I get a 1 for the first entry. Then if I do 1, 1, 1 times this column, I get 0, and 1, 1, 1 times this column, I get 0, so that's fine. If I take 0, negative 1, 0, I'll get 0, 1, and 0, and then 0, 0, yeah, okay. So actually, P inverse is not P transpose, because these are all 1s and negative 1s. P inverse is actually just P. So that's kind of neat when trying to make that happen. But so let's check P times D times P then, since P is P inverse. Okay, that's 1, 1, 1, 0, negative 1, 0, 0, 0, negative 1 times D, 2, 0, 0, 0, 1, 0, 0, 0, 1. Okay, our diagonal matrix with eigenvalues in it, and then times 1, 1, 1, 0, negative 1, 0, 0, 0, negative 1. Okay, if we do these two first, I'll have 1, 1, 0, 0, negative 1, 0, 0, 0, negative 1 times, okay, I get a just 2, 2, 2 across the top. Then these are identity elements in the bottom, so I'll get 0, minus 1, 0, and 0, 0, minus 1. And so now this multiplication, I get a 2, and then the 1, 1, 0 times the middle column, I get a 1. I get a I get a 2. Is that right? And then the others, I would have a 0, 1, 0, 0, 0, 1. So I feel like I have a miscalculation here, because I believe that should be a 1, shouldn't it? For my A. Yes, that should be a 1. Let's see. 2, 0, 0. Yeah, that looks like that should be 2, 2, 2. Negative 1. Yeah, and negative 1. That looks good. And then the top, I get a 2. Oh, silly. Okay, and so that is indeed a 1, which is A. Okay, so that worked, and we were able to diagonalize A, as this set of matrices. So that was a 1. Okay, so there we could do it. Now, all I have to do is actually switch this. If I now say B is equal to 2, 1, 1, 0, 1, 1, 0, 0, 1, then here, again, our eigenvalues are lambda 1 equal 2, lambda 2 equal 1. Hopefully I've convinced you that, yes, I can just read those off of there. And so they have the multiplicity 2. Now, if we look at lambda 1 equal 2, again, we get a 0, a 1, 1, 0, minus 1, 1, 0, 0, minus 1, augmented with 0, 0, 0 when we let lambda 1 equal 2. And here, when we do that, then I can add row 1 and row 2 and put it back in row 2. And I get 0, 0, 2, 0, and 0, 0, negative 1, 0. And so once again, what you see is that 2, I can turn it into a 1, and I can get rid of that, and I can get rid of that, make them zeros. And so I get that same x1 is equal to the vector 1, 0, 0. Okay, because again, x can be, that first component can be anything, but the other two are at 0. So now let's look at our lambda 2 equals 1, and in that case, we get the 2 minus 1, so we get 1, and then 1, 1, 0, 0, 1, and 0, 0, 0 when we subtract down the diagonal, subtract 1, and this is 0 and 0. But now notice what happens when I row reduce this. You know, that this 1 down here is going to get rid of the 1 up there, and so our reduced row echelon form is this. And so what that says is now x equals minus y, but z is stuck at 0. And so we see the rank is 2, so the nullity is 1. And so the nullity of A in this, of B is equal to just 1, which is less than 2, right? And 2, though, was our multiplicity of that eigenvalue, okay, just like it had been before. And so we've got a problem, okay, and B is not diagonalizable, in this case, okay, because I can't find a second vector because the nullity is just a dimension 1. Okay, so my eigenvector here, I didn't write that down, my x2, x has to be minus y, so I could do a 1, minus 1 again, but that has to be 0, and I'm just stuck with that, and so I cannot create my matrix B from just those 2 columns, right? Because those are the only 2 columns I have. So I don't have a P matrix. P doesn't exist. Okay, because I need a 3 by 3, and all I can get is a 3 by 2. I can only get 2 vectors. So that is the idea of this theorem. Okay, is that if the nullity matches the multiplicity, of the root, we can still come up with a diagonal representation for our matrix. And so that's theorem 6.2.3.